Greetings, folks. Professor Fiore here, and it's time to revisit our earlier LED bar graph video. If you haven't seen it, that's in the Op Amps playlist. It's an all analog version of what we're going to be talking about. I'm sure you're familiar with the idea of an LED bar graph, right? We see them for audio levels. We see them for, speed of different devices, temperature, pressure, things like that. It's something you can look at quickly, get an idea of what it is. It's not super high resolution usually, but it's something that is very useful if you have a fluctuating kind of signal. Okay, so we are going to do something a little bit different here. We are going to program the Arduino to do this. Functionally, this is going to do all the stuff that our analog version did. And if you're really not familiar, it's a useful thing. Go back and look at that video. It essentially uses a string of comparators to do this. And if all you need is a simple kind of bar graph, nothing fancy, that actually might be a better route rather than dedicating an entire microcontroller to this. But as you're going to see, there are things we can do using the microcontroller that are kind of difficult to do with an all analog system. So, there's an upside, there's a downside, all right? Essentially what we're going to do is we are going to use the analog input port. I've set this up to use an Arduino Uno, standard kind of thing. And that input port, that's going to be an analog input. In other words, we're going to use the analog to digital converter. Our input signal is going to go in there, and then we're going to write to multiple digital output lines. Important thing, I am not going to be using the standard Arduino library digital write function. That's write out. We're not doing that. We're going to do some direct writing like the way we would in any generic microcontroller. This will be much, much more efficient. You'll see exactly what I'm talking about when we look at the code. The code, as it turns out, this whole thing is based on lab number 9 in the Embedded Controllers lab manual, right? So you want to take a look at that. In that particular lab, we used a force sensing resistor, and we created a 4-segment LED bar graph. We can go beyond that. I'll show you how this works. One caution, and that is because of the way this works, we really need a front-end circuit, a wave shaping circuit, to get a proper display. Now we can also sort of piggyback on that. We can get voltage gain out of that front-end circuit if we need it, and it can also supply high input impedance buffering, right? So that's a good thing. Let's take a look at that code. Here is the code that we used for that little FSR 4-segment bar graph. Now, I'm going to change a couple of things here. Very importantly, I want to jump out and say this code is actually more complicated than it needs to be if we're doing something like an 8-segment LED display. Why do I say that? Because an 8-segment display can use an entire port. You say, I'm going to use all of port B. And as you'll see, this code would shrink down, right? But this is only going to use 4. We're only going to use the 4, right? So I'll show you just exactly how we can go about doing this. Now, if you wanted to use higher resolution, in other words, you want 12 segments or 16 segments or something, then you'd have to get a couple of ports and write to those, all right? No biggie. A couple of minor things with formatting here. For some odd reason, Tina TI did not like the single vertical bar character that we would use, for a bitwise OR. So I had to settle for this little character here. When you see this, that's all it means. It's just the bitwise OR symbol. Also, the asterisk symbol that we would use for a pointer just shows up in this font as a little dot. So you got to keep your eyes close on this. But this is really just that same code. I've done some slight massaging to it to make it look a little bit nicer, to take out some things we didn't really need. But, grab the lab manual, hey, it's the usual free OER. Just download, go to one of my sites. The links are in the video description. But in any case, let's follow through and see what this is going to do. This is the bar mode, right? Using, like I said, 4 bits of port B. All right. So in our setup, we simply set up the ADC part and the output. So we set the analog reference to the default, and then I set the driver bits for the output mode, right? I've got one LED mask 0, 1, 2, 3, one for each of the outputs, right? 1, 2, 4 in hex. And then this thing called LED mask is just that set of them. And this is just a convenience. So we don't have to keep writing this, right? So the loop doesn't really do too much other than it reads the ADC, the analog to digital converter, sets that to the variable A, and then it compares it to a prior value, which I just have a global over here, right? It's just a quick and dirty kind of way of doing this. So we set that value to 0. If there's a change, we simply come in and light the LED, right? Remember, the output pins are going to stay at whatever level we set them at. I don't have to keep refreshing them. So, initially when this thing comes up, everything's at 0. So we're going to get a read on this thing. We're going to get a signal, and we would light this up. And then for the next time around, we reset prior to its current value. So the fun function really is this thing called light LEDs bar, right? We send it the value that we're looking to light up. So here we only have 4 segments, and the ADC is a 10-bit ADC, so that goes from 0 to 1023. So all we've done is we've chopped this into essentially 4 segments. And what I do is I look first at the highest level, and I've hard-coded these. In a second, we're going to look at a better way of doing this, but I've hard-coded it to make it obvious. So we're saying, okay, if the ADC comes back as 820, right? If it's above 820, then let's light all of them. So we just blast into port B the LED mask, right? In other words, we OR in those 4 bits, right? We OR in these 4 because that's LED mask, which is just the ORing of these. Right? Light everything. We're done. Of course, we do it this way because we don't want to mess with the other 4 bits that port B might be used for. So this is one of those places where I was talking about earlier. If you're going to use the entire port, in other words, you have 8 segments, you don't have to OR anything. You just say port B gets LED mask, and that's the end of it. All right? You just put the number in there, and you're done. All right, so if that's not the case, in other words, if it's less than 820 or 820 and less, we then check to see if it's at least 615. If it is, then we extinguish the topmost, right? So we do the usual bitwise AND with the complement. So that gets rid of that bit, and then we just blast in the bottom 3 bits. Again, this would just be a simple write. I would simply have the mask that I need for the bottom 7 if we were doing the entire port. In other words, all 8. Okay, so you're going to see these sort of clear write kind of things, these pairs. When in fact, if you're going to use the whole port, you just need one assignment statement, and that's the end. But this process just continues, right? We then look for the next level. If it's not above 615, we check to see, is it above 410? Okay, that would be the bottom couple. So let's turn the bottom couple off, turn the other 2, turn off the top 2 and turn on the bottom 2. And then finally, well, not quite finally, right? Penultimately, if it's at least 206, right? 206 and above, then we would extinguish the top 3, just turn on the bottom one. And if it's 205 or below, we turn off everything, right? That's it. That's all we have to do. So then the next time through, the loop comes around. If we have, a different value, we just run this again, okay? And there's the LED, right? Simple. Now, bar mode, a little bit different. Not a lot different, but a little bit different. But there's another thing I want to show you in here, and that is, instead of hard coding these values, there's a nicer way of doing this. Okay, so a lot of this is the same. I have the same LED mask. I'm still using 4 bits. okay? But instead of hard coding those 4 values, I put them in an array. Now, what I want you to imagine here is having multiple arrays, a threshold 1, threshold 2, threshold 3, and so forth. So you might have one that's, okay, I have a linear setup for this. I have a 3 dB logarithmic setup for this. I have a 1 dB logarithmic setup. I have a 6 dB setup. You could have bunches of these things. Then you could have some external pins where you have switches and so forth, and you can select which mode you want this thing to run in, okay? In our case, I just have the 1, and I'll point out where we would sort of monkey with this for different kinds of modes, okay? So again, setup, no change there. We go in the loop, really no change there, except in this case, I'm calling LEDs, dot mode. And by the way, if you want to do both, you would have an external pin there that you would set. The user would set for dot mode or bar mode. And right in here is where you would have a little if test. If it's high, we'll do light LEDs dot. If it's low, we'll do light LEDs bar. Okay? All right, so here's light LEDs dot. And this is the same kind of format that we had in the light LEDs bar function. All right, so I'm going to call up a pointer, and this is another weird little thing that happened in Tina's text thing. The asterisk just turns into this little dot, right? This little dot. So that's, this is a pointer, and over here, this is value at P, incremented. All right, so in any case, what we do is I'm going to set this pointer to thresh. In other words, the array of values. So if we had a choice, right here, we would have a little if, and I would set P to thresh 1 or thresh 2 or thresh 3 or, whatever it was, right? That's way better than going through and, creating a whole set of functions for, these numbers and another set of numbers and another set of numbers. Oh, it's easy for me to do with cut and paste. Yeah, but it's confusing and it's very inefficient. So just do this, right? It's a lot nicer. So anyway, we check the input value. Is that greater than the value at P? Increment it for the next hit, right? The next test. So what we do here is a little bit different. We turn off the bottom 3, right? Whenever you see this anding with complement, you're turning it off. And then we OR this to get the topmost, right? So only 1 LED. I don't know what was on before, right? That's why you have to turn off all of the other ones. I mean, maybe the last thing I did was, 1 level below. So I need to turn that off. I don't know what it was. So we have to turn all those off, turn this one on. Then we check the next value at the pointer. Now, if you think in terms of the array, this is essentially thresh 0. This is thresh 1. This will be thresh 2 and thresh 3, right? So now I'm looking at the next value. And in this case, we're going to do the same thing. We're going to turn off a bunch of the LEDs. But in this case, there's some that are above and some that are below. And then here's the one I want to turn on, right? This is the dot. And we just continue on down here. Check the next level. That's the dot. Everybody else gets turned off. Check the next one. This is the one that's on. These are off. Otherwise, everybody turns off. Okay? Beautiful. So that's all you have to do. Now, there is an interesting problem with an AC signal. And that is the fact that this process that we're looking at is called a time discrete process. The all analog implementation, the one that you find in the op amps playlist using comparators, that's a time continuous function. In other words, the instant the input changes, the comparators react, and then the LEDs react. That's not what happens here, right? When you go through the loop at some regular interval, I don't know what it is, at some regular interval, this thing is going to be called, right? We're going to check the analog read, and then we'll, if we need to, light up the appropriate LEDs, okay? Now, when you have this sort of time discrete or time discontinuous kind of process, this opens up the possibility of something called aliasing. So let's say we have a sine wave. This is my very simple input, right? I'm not going to use like a fancy audio signal. This is just a sine wave. So the comparators would be looking at this continuously, right? Always, always, always. And the instant we get a change, boom, the LED is going to light up because the comparator is going to flip. But here, I don't really know necessarily when that ADC is going to be called. Now, even if you set up an interrupt service routine to do that, and you actually know at a regular interval, that doesn't sort of help you, as you'll see in just a sec. So let's say that, every, 2 or 3, let's say milliseconds, just to keep the numbers easy, and I can use my scale here, the ADC call is performed. So you get a value right here. Let's say right at the beginning is your first one. So you get 0. All right, nothing gets lit up. And then, 2.1 milliseconds later, you get another call. So that's like around here, and you get a certain number. And then, maybe, like 4.1 milliseconds later, you get a call over here. You get a value here. The next one is over here. The next one's up here. The next one's over here. It's kind of odd that you would actually hit the peak at any given point. I mean, you might, okay, but not necessarily. And, something really weird can happen. Even if you have this thing on a regular ISR, an interrupt service routine, it just might work out that you always take measurements at the same point in the cycle, So, it's a 1 kilohertz waveform. Okay, I just happen to have my ISR every millisecond. So whenever it hits this point, boom, that's what I take my measurement. It's not going to be accurate. I need a way of sort of stretching this out, some way of improving my odds, if you will. That's one way of looking at it. Okay, I'm going to need a front-end circuit for this. So here's something you can do. We can go to a precision envelope detector. So this is a precision half-wave rectifier. All right, and then what we do is we add a little cap on the output. And this, on the falling part, in other words, this is going to charge up really quick, but once the signal falls back, right, and the output on this goes below whatever the cap is charged up to, this diode is going to prevent really the discharge of this cap. So it's going to hold that value. So if you have a signal coming along here and there's a big spike in it and then it drops back down, what's going to happen is the cap will track that, but instead of dropping down immediately, you're going to get this RC time constant, which is going to stretch that out. All right, and that can kind of bridge the gap between the individual cycles. If you want to be really nice about this, you could put a precision full wave rectifier up front so you can see both the positive and the negative pieces, right? But just to show you how this would work, right? We'll do a little transient analysis here. And what I've done is instead of using a standard input signal, I have chosen a wave file. And the wave file that I've got in here is, in fact, a little voice waveform, okay? And we can hear this little voice waveform.
Put that thing away.
All right, so that's the waveform that's going to go through here. We're going to see exactly what it is, right? This is exactly the sort of thing you're going to see if you're going to use, this application for an audio signal. All right, that's a real live audio signal. So let's do a transient and see what happens. I'm going to look at 1 second of that little voice. Okay, let's bring this over here so we can see it. And we'll take a look. All right. We're getting some overlay on here. So this green is the input signal and the output is the V load. This will be a lot nicer to see when we split them out. Okay. So here's my input signal. This is set up for a 1 volt peak. All right. And if this is like totally new to you, I do have a video that shows how to use the wave file input for an arbitrary signal. But this is our input signal. And what's happening here is we're getting just the positive part of it, right? Because of the diode over here, the precision half wave. And then what's happening is the cap is then sort of filling in the gaps, right? Because otherwise all these things would be going back down to ground, all right? But instead, you can see it's really kind of filling this in very nicely. You can see these sort of sharp little lines, and you can adjust this by the size of the cap. Some places it's kind of obvious what's going on, like right here. You can see that cap discharge. Matter of fact, we could sort of zoom in on this a little bit. All right, so that's the cap discharge coming in, all on all of those things. And you can just compare that to what the input signal actually looks like. We have different scales, right? But this is essentially the positive piece of this. It's grabbing these things and sort of filling in the gaps, right? These spikes are these bigger ones, and then the cap is filling that in. So if we had a larger cap, that would make it a little bit more full. You wouldn't see quite so much, I guess I'll just call it ripple, right? It would track this a little bit more closely, but that's just something you have to play with, right? You know, what's going to work in your particular application. All right. So we've got code, we've got an input circuit. Bingo, we've got ourselves a microcontroller version of our LED display, bar graph, dot graph, whatever you want to call it. And like I said, this version, a little bit more complicated, but definitely more flexible. Okay, we'll see you next time. Hope you enjoyed it.